it just a minute. Let me clearing from this page. So I had to start this over. So I messed up. Oh goodness. Right there. Since I do a terrible job of showing what these look like, it might be prudent of you to go ahead and look in your textbook as I'm discussing what these graphs look like. But a logarithmic function, the reason we're talking about them now after talking about the exponential functions is because they are inverses of exponential functions. A log base 10, his inverse would be an exponential growth, who also happens to have a base of 10. And a natural logarithm, remember, is a log base e, so his inverse would be an exponential growth of base e. Only logarithms that you can do on your calculator are the common log of base 10, or the natural log, which remember is a log base e. It's natural log, ln. I don't know why it's abbreviated ln. I'm thinking it's something to do with the French derivation of the original words. So anyways, this is where I'm referring. I'm going to do a really cruddy job of graphing these for you, but if you look in your book on page 347, you're going to see that the logarithms, depending on what type of base they have, could look like two different things. It doesn't matter which type of logarithm you have, but the general logarithm will always have a vertical asymptote at the line x equals 0. So for both of these, they're going to have a vertical asymptote at x equals 0. For a base between 0 and 1, so for instance, if you had a log of base 1/2 of x, he is going to be the inverse of an exponential decay, if you can kind of visualize what that looks like. Exponential growth or decay used to go through the point 0, 1 when it wasn't shifted at all, so his inverse would go through the point 1, 0. And when your base is what used to be a decay base, your logarithm is actually going to end up looking kind of like this. So again, apologies for how terrible my logarithm looks. However, if you have a logarithm of a base that's greater than 1, for instance, log base 5 of x, still going to go through the point 1, 0, but this time, because he's the inverse of an exponential growth, you're going to see something that looks more along lines of this. So two things I want to point out. The x-intercept is similar to how we used to identify the y-intercept for growth and decay, but both of these logarithms are going to always have a vertical asymptote, which is generally at x equals 0 unless there is a horizontal shift. The other thing I want to remind you about from Algebra 2 is logarithmic form and how you can convert from that to exponential form and then vice versa. So the first thing I do is when I have a logarithm, if I have to convert it to exponential form, I identify the base. The base of the logarithm is the small subscript, so base is 2. He's going to also be the base of the exponential problem. And then the way I kind of remember it is the next two numbers just basically flip. So it'll be 2 to the x power equals 8. I'm sure your Algebra 2 teacher had a cute saying for how to remember that, but I think you know it by now. So number 4, identify the base. He's a 25. And then raise it to the 1/2 power, and it equals x. So that's the equivalent exponential form of that logarithm equation. Now going the other direction, an exponential problem rewritten as a logarithm. So I write down log, then identify the base, who is very easy to find. He's a base 3. And then remember these numbers just kind of switch. So log base 3 of t equals a. And then the next problem, it's not quite an exponential form because I need you to rewrite it. So it's 3 equals, the square root is really a 1/2 power. So I'm going to say log, I can see now that the base, the guy who's holding the exponent up, is a 9, so log base 9. And then 3 and 1/2 will just kind of switch spots. So log base 9 of 3 equals 1/2. I tend to be, it's easier for my brain to think about log to exponential, so generally when I get an exponential to log, I quickly reverse it in my head to make sure I did it right. Now this next section, we're going to solve a logarithmic equation for the variable. There's so many different methods, and they're all really the same thing. So we could rewrite them in an exponential form. We could use logarithms. Later we could exponentiate, change a base. They're all really the same thing. But what I'm going to show you is how I always teach my Algebra 2 kids, because I think it's the most effective, because it really tells you what you're doing, and it's how you're going to do it in college. The way you undo a logarithm is you exponentiate. So what that means is you identify the base, and you raise the problem up to that from that base. So if it's a base 4, I'm going to shove a 4 underneath both sides of these of this equation. So what I really have right now is 4 to the y power equals 4 to the log base 4 of 16. And the reason this works is because on this right-hand side, 4 to the log base 4 of 16, from the inverse properties of logarithms, I know 4 to the log base 4 will cancel. So all I really have is 4 to the y equals 16. Now if I think about that, because I think I don't have to do any more algebra, 4 to what power would give me a 16? I'm guessing y is 2. If that one wasn't so easy to do in my head, I would have had to apply a common or a natural logarithm at that point. But there's other methods to solve that. They're all really the same thing, though. They all come back to the same formula, which derives from exponentiating. So here on this problem, we're going to exponentiate with the base of 5. So my problem is really 5 to the y equals 5 to the log base 5 of 12. So again, 5 to the log base 5 cancels. I have 5 to the y equals 12. Unfortunately, this one is not going to be so easy to solve in my head because I don't know what power I should raise 5 to. So I need to bring the y down by applying a logarithm. Because I'm going to use my calculator, I only want to choose a common log or a natural log so I can actually use my calculator's buttons. So I always choose natural log because it's one less letter and I'm lazy. So the y will come down. You've got y times the natural log of 5, which is just some gross number, equals the natural log of 12. So to solve for y, remember this is just a number. I'm just going to divide by natural log of 5. And you're going to type this on your calculator, but make sure you're wary of the parentheses. So make sure you close the parenthesis after each logarithm's number. Natural log of 12 divided by natural log of 5, and then whatever decimal that came out to. Okay, number 9, we're going to exponentiate with a 3 this time. So 3 to the log base 3 will cancel, and I get x equals 3 to the negative 2 power. Well, that's just a computational thing. That's the same thing as a 1/9. So x is 1/9. And then here, if you want to think about exponentiating again, I would exponentiate with an x. So x to the log base x cancels, and 1,000 equals x to the third. I would solve that by cube rooting both sides. Turns out the cube root of 1,000 is nice. It's 10. Same thing here on number 11. I'm going to exponentiate with an x. So these will cancel, and I get 3 equals x to the 3/4 power. Well, I know from algebra to undo a rational exponent, I'm supposed to apply the reciprocal power. So 3 to the 4/3 power is what I'm going to type in my calculator. Let's see. Cube root 481. I think it's a 27. Let me check. No, it's not. It is a decimal. So it doesn't say how to rewrite it. If they wanted the exact answer, I'd say 3 to the 4/3 power, but a 4.33 is a good answer. And then I can't read this. I think it says log base e, which tells me e to the log base e or e to the natural log would cancel. I have square root of x equals 5. And then I'd square both sides and get x equals 25. Okay, properties of logarithms. First property is the main property of a logarithm. It says that if you have a log with a base of whatever, anything, and a number raised to a power, the whole point of a logarithm is to bring that exponent down in front. So that's what the first property is showing you. The next property says if you have a multiplication problem inside a logarithm, you could expand it into the log of the first number plus the log of the second number. And then the third property is the quotient property. Similar, except now it's division, so we're going to expand it by doing the log of the numerator minus the log of the denominator. So if we're going to expand number 13, I see it's the power property. So this x is going to come down in front, and I have x times the log base 3 of 9. Now, the log base 3 of 9 is actually some number. I always taught my kids to think of it as 3 to some mystery power equals 9. Or you could remember the change of base formula, which says you could do the common log of whatever the number is divided by the common log of the base. So a thinker or a calculating problem, I don't care. The answer is a 2 for that, so it's really x times 2. So this simplifies down to a 2x. Number 14 is a multiplication property, so we're going to separate it into the log base 2 of 4 plus log base 2 of 32. So again, you could either use change of base on your calculator, or you could just ask yourself, 2 to what power gives me a 4? That's a 2. And then 2 to what power gives me a 32? And that's a 5. So 2 plus 5 is 7. And then the quotient property, log base 5 of 1 minus log base 5 of 5. So 5 to what power gives me a 1? That has to be a 0. 5 to what power gives me a 5? That has to be a 1. So the answer to that question is negative 1. Now we're going to just condense and expand with algebraic terms, so we're not going to get a single pretty answer. Well, some will be single, but they won't be that pretty. So condensing, first thing I want to do is throw my exponents back up where they belong. So this is really log of x squared, it's the common log, plus log of y. And the addition, or the multiplication property says when you have an addition of two logarithms, you bring them together as a multiplication problem inside of the one logarithm. And I like to use parentheses around what's inside the logarithm. There's no exponents to bring up in this next problem, but they're all going to be brought together. Whoops, I'm going to hold off on that one. Through quotient or multiplication properties, product properties. So this is log base 3 of, it'll be 4x when I multiply them together. And then if I try to bring together the subtraction problem, that is now the quotient property. So it's the log of that's the numerator, and then the denominator. Oops, and I forgot a very important part. He was a base 3 logarithm. If you forget to write what base he is, you're actually ruining the whole problem, so be careful. Now number 18, we are expanding. I see a multiplication, 3 multiplications actually, and then an exponent that we will bring down once we have that log isolated. So first I'm going to separate it into log of 3 plus log of x plus log of y squared. And then final step, this exponent comes down. So final answer, and you guys are probably really good at this now. This is your second time around seeing these topics. So you might find that you don't have to show every intermediate step, and that's okay. This question's a little tricky because there's a division of 2 things. So we're going to first set up the division problem as a subtraction problem. And then I know one thing that's going to have to happen is this exponent will come down, but this is the part I'm worried about. We're subtracting a log base 5 of y and z, which means when I separate the y and z, I got to remember to subtract both of their logarithms. So I have 3 log base 5 of x minus log base 5 of y, also minus log base 5 of z, and that is fully expanded. Well, I guess that was it. Short lesson. So it should be a good review of what you knew back in Algebra 2, and we're just going to go further with it. So after this, we have logarithmic models.